intermolecular forces of attraction. So if you got your notebook out, you can get that out, and we'll get going. Won't be really much time for discussion. Okay, so we're just strictly talking about molecules, and this is supposed to be the last part of Chapter 6, and sometimes we get it in, and when we do get it in, there's just a lot of information for Chapter 6 tests. And so the past couple of years, we've just kind of waited and kind of done this later because it does take some time in which to do the lab that goes with it. That kind of extends the chapter, and then you forget some things at the beginning of the chapter, and so I have decided to shorten it up. So molecules will attract one another to a certain extent. All molecules attract one another. Some attract one another with a greater force, and others with a less force. Kind of like magnets, you have different size magnets you could have, different strength of magnets, magnetic field forces. And molecules would be the same way. So the first thing we'll talk about is something you know a lot about already, and that's why it went with this chapter. The first one we're going to take a look at that's listed under these forces is dipole-dipole interaction. So what creates a dipole from what we talked about when we talked about bonding? What do you think, what kind of bond will present a dipole? So there was different ways you can determine if something was a specific type of bond based upon electronegativity. So what kind of a bond would create a dipole in a molecule? Okay, last chapter, a dipole is when you have one side slightly positive of the molecule and one side slightly negative. That's a dipole. Okay? So what would create a situation where one side is slightly positive and the other side slightly negative? Polar bond. So we're not going to take a look at ionic, because that's greater than 1.7. So what creates a dipole is where you have one side of the molecule slightly negative, and one side of the molecule is slightly positive. So that would be a difference between 0.3 and 1.7 is what you'd have. So if we go ahead and take HCl, for example, we know it's a single bond. I mean, if we would go through the structure and do it, we'd have a single bond. So these electronegativities that you have, that you deal with, when we have HCl, H is 2.1 and chlorine is 3. So I'm just going to put 2.1, and this is an electronegativity of 3. So which of those two have a greater, which of those two will have a greater pull on that electron, chlorine or hydrogen? Chlorine does. So the pair of electrons that are shared here are not equal. They're unequal. And because of that, chlorine has a bigger share of those electrons. So it's going to take on a slightly negative charge. And hydrogen, because it's giving up more of its electron than it originally had, then it's going to take on a slightly positive charge and creates a dipole. Okay? Opposite charges on ends of a molecule. So what we're going to do is we're going to show an arrow. Okay? When we show an arrow, okay, and that end should be more of an arrow. That end is going to be slightly negative. See, I'll go ahead and rewrite that again so you can see it better. So this end is going to be kind of, you know, on arrows they have the free feathers at the end to kind of guide it. Okay? And then you've got your head of your arrow. So this side's going to be slightly negative here. And then this side's slightly positive. So my pin's a little off because I think it got off kilter. I'll have to readjust it. But this side's slightly positive and this side's slightly negative. So that creates a dipole situation. Okay? We'll go ahead and show you how those might interact if they're a dipole-dipole interaction. Okay, we'll show you a couple examples here. So this side of the arrow is slightly negative, and then this, or molecule, and this side is slightly positive. So what do you know about opposites? When we get a molecule, we've got one side slightly negative and the other side slightly positive. What are they going to do? They're going to attract. And so we show an intermolecular force with dotted lines because they're usually not as strong as a covalent bond or ionic bond. So we'll show attraction between those opposite sides. Just kind of like north and south side of a magnet, same idea. If there's going to be attraction between those two areas. Okay? We can even show it here. So, any questions with that? So there's lots of those floating around. And what's one way that they can interact? If they're a polar molecule. Okay? If they're a polar molecule. I'll give you another example of a polar molecule. We got trigonal pyramidal for ammonia. Okay. Nitrogen is going to be free, where hydrogen is 2.1. So which direction will the arrow go there? Go towards the higher electronegativity. So the arrow always goes toward the higher electronegativity. So we would show free arrows. You guys do a better job than me. Okay? This side of the molecule, I'll go ahead and redraw it down here without the arrows. This side of the arrow here is going to be opposite of this side. So what's the charge of this side of the molecule, the nitrogen side? What's it going to be? Slightly negative, because it has a bigger share of all three of those pairs of electrons, and this side is going to be slightly positive. So if we had to rewrite that and show how those attract, you guys don't have to show all of these. I just want to give you some information to be able to look at. There's going to be attraction here between the nitrogen and the hydrogen because they're opposite charged. Again, this side's slightly negative. This is the bottom portion of that pyramid. It's slightly positive. Same here. Negative, positive. Okay, any questions with that? Now, is there a situation where we have a nonpolar molecule? Sure, we can have a nonpolar molecule. For example, if we have Cl bonded to Br. It's a nonpolar molecule because chlorine is 3 and bromine is 2.8. Okay, we wouldn't show an arrow for that. So this would be a nonpolar situation, nonpolar molecule. Another situation would be if we had P bonded H in a trigonal pyramid. Phosphorus is 2.1 and hydrogen is 2.1. So that would be a nonpolar bond. So that's a nonpolar molecule. So these are nonpolar molecules here. There's one case that I'm going to share with you where we have polar bonding, but we don't have a polar molecule. So underneath this, I'm going to go ahead and show you another nonpolar molecule. Okay? And then what I need to transition to is hydrogen bonding before you go. So any questions you have up to this point in time? You have to have a polar bond. And if you have a polar bond, it's most likely you have a polar molecule. Most of the time, you're going to have a polar molecule. And because you have polar molecules, you'll have one side slightly positive, the other side slightly negative, and there'll be a slight attraction between those molecules when you have that. All right? Here's a situation where we have polar bonding, but we don't have a polar molecule. So this goes under nonpolar molecule. So chlorine is 3.0. I'll just show one of them. I'm not going to show all of them. And carbon is, I think, 2.2. Okay, let me double check that. Yeah, it's 2.5. So 2.5, what's the difference in electronegativity? 0.5, right?
Yes, sir.
So that'll create a little bit of a polar bond, but not real big. I mean, the bigger the difference, the more polarity you have. So we would draw our arrows like this in all those cases. So this down here is negative. Down here it's negative. What's it above? Negative. Everywhere you go around that molecule is negative. So really there's no difference in charge on one side of the molecule. It's all negative on all sides, so because it's all negative on all sides, it doesn't create a difference in charge. We don't have a positive or negative end. Okay? So this would be a nonpolar molecule. Even though we have polar bonding, they all cancel out. All right, any questions on that? So most of the time, if it has polar bonding, you're going to have a polar molecule. And the bigger the difference in electronegativity, the bigger polarity you have. So the bigger, if it gets up to like 1.6, 1.5, bigger difference, more polarity associated with that. Any questions with that? All right. Second one, number 2. It's called hydrogen bonding. So what do you think, what element's going to be involved in this? Probably, it is oxygen. You're right, but it has to be with hydrogen. Okay? So, hydrogen has to be bonded to 3 elements so we can have hydrogen bonding. So we're still under what's called intermolecular forces of attraction. The first one's dipole-dipole interaction, where you have opposite charged sides of a molecule. Then you got hydrogen bonding, where hydrogen is bonded to one of 3 elements. Okay? So what's needed is hydrogen is bonded to, that's not the hydrogen bond though. Okay? For this hydrogen bonding to occur, hydrogen has to be bonded to one of 3 elements. So if hydrogen is bonded to one of those 3 elements, then we can possibly have and probably have a hydrogen bond occur. So I'm going to show you a couple examples of hydrogen bond, give you the reasoning for that, and then we'll be done. Okay? So if we have H bonded to oxygen like this, that would be hydrogen bonding. Yep, water has hydrogen bonding. Okay? The hydrogen bonding we're talking about is not these two spots. Right? So if we would show the dipole-dipole interaction or show the polarity of it, it would go like this, like we did before, with dipole interactions. Okay? So what we know is that there's 2 unshared pairs of electrons down here. If we have another molecule down here, just like that one of water, then the hydrogen bond occurs with they're going to be attracted to these electrons because this side of the molecule is positive and these 2 electrons are negative, unshared pairs. So it's an attraction between the hydrogen and an unshared pair of electrons. So these electrons we're showing will be attracted to the positive hydrogen. So that's what hydrogen bonding is. It's an attraction for an unshared pair of electrons. That's what hydrogen bonding is. Is the attraction of H for a pair of unshared electrons in another molecule. That's the only way we can have hydrogen bonding. Okay, I'll give you one more example of that. The worksheet that you have, tomorrow, those that are here, we're going to go through how to solve for drawing the structure, finding the molar mass, and see if it has hydrogen bonding or not, based upon that. That's what we'll do tomorrow. Plus, we'll look at what's called London dispersion force tomorrow, a little bit, because you'll have to know that information. Let me show you another example of hydrogen bonding. H is bonded to F. So we got that. That works. And now H will be attracted to that unshared pair of electrons. Okay? Do we have hydrogen bonding here?
No.
There hydrogen bonding? No, because it has to be bonded to F, N, or O. So that doesn't fit the requirement. So we don't have it there. What about hydrogen bonding here? We do. Okay? Because this nitrogen down here we'll get it. Okay? So it has to be attraction for an unshared pair of electrons. If there's not any unshared pair of electrons in another molecule, there won't be any hydrogen bonding that can occur. It has to be attracted to an unshared pair of electrons. Okay?